Hi there. I'm network engineer at Facebook, and I'm here today to talk about how we built our edge networks at Facebook. And I'd like to go on a journey and give you an idea not just of the technology we've built, but also of the culture and our approach to problem solving. Facebook is huge. Everybody knows that. When you have more than 1 billion users, you know that the scale of the network is enormous. But what I'd like you to see in this graph are these little strands of light representing connections between people, and particularly how bright this graph is all around the world, not just in the United States. And that's because our products are global services. More than 80% of our users are outside the United States. And ultimately, all of them connect through our edge networks. Now, I'm sure as the people in this room can appreciate only too well, networks are very easily taken for granted. They're a lot like oxygen. When it's there, you don't even think about it. But when it's not, you feel it immediately. Now, that's true for networks in general. It is certainly true for our edge networks. When they're not where we need them, when there's not enough of them, we're strangling our services. So what is this service that we're providing through our edge networks? Part of our service is very similar to other CDNs, static content, saved photos and videos, which are very cacheable. But there's a component of our service that is unique, a bit different. It's the dynamic component, the status updates, the comments. Whether you click the like button, there might be a star that you really like and that you want people to know about, or maybe not. But let's assume that you do. Whether you're clicking like on your friend's post about their new job, whether you're clicking love about the picture of their new child, or expressing sadness about the loss of a good friend, fundamentally we're providing a communication medium. And this dynamic data needs to be true, it needs to be right, not just for your friends in the US, but for everybody you know around the world. So I'd like to take you on a journey down memory lane. 5 years ago, our service and our network were very different. If you connected to one of our services, your TCP connection would actually terminate on a server in a data center all the way back in the United States. Now, if you were in the US, the performance of the service was kind of okay, but in much of the rest of the world, it was terrible. Now, let me give you an example of this. If you connected from, say, somewhere in Asia to a data center in Oregon, your TCP round trip time might only be 150 milliseconds. But if you expand that out to a full connection, pulling down real content, it's actually more than half a second just to get your first bit of real data for your web page. And if you take that across the rendering of a full page with rich content, it's a terrible experience. It's extremely slow. It's unacceptable. So we needed to build not just edge POPs, edge routers for network connectivity. We needed to build edge servers to terminate those TCP connections closer to the people who use our services. And by doing that, we dramatically improved the performance of our service around the world. Yes, those dynamic pieces still need to be synchronized back to data centers. That content still needs to be pulled, but now it's proxied through always-on connections from our edge servers. And those TCP connections, that slow part, is now very fast. What was poor performance is now pretty good performance because of this. So what does this look like from a network perspective? We began with simple edge routers and POPs for network connectivity. This grew to edge servers hanging off of these routers to terminate those TCP connections. And that solved the problem of the basic Facebook landing page, improving performance for rendering that basic framework. But as our product changed, it became more rich, more photos, more videos. The demands on the network changed. And fortunately, we were ready for them. As we built out more servers, we grew to full edge clusters and cross fabrics to aggregate these servers and support east-west and north-south traffic in every edge POP in the world. And today, our service is different than it ever has been before. Video is growing. You may have seen the growth of our live broadcasts over the last year, whether it was Mark's broadcast with the space station or the recent presidential debates. This is a fundamentally different type of service in that it's very spiky. At a moment in time, from out of nowhere, hundreds of thousands of people, potentially millions of people, watching the same content at the same time. We needed to build a different type of network to support this. And so what we build today are actually multi-layer edge topologies. Of course, 100 gig everywhere. Because of our space and power demands, we grow across multiple facilities, peering facilities, large facilities for aggregating our servers, connecting to our backbone. And to grow independently in these different layers, we needed to disaggregate our functions. The old topologies, simple router God boxes connected to the backbone peering and to our servers. Now we have different functions for connecting to each of these layers that allow us to grow independently and more simply. But at the same time, we need to reconsider how we build our networks from a protocol perspective. So I'll talk in the next few slides about how our software stack has changed and how it has allowed us in many ways to evolve beyond the limitations of BGP. Now, the world runs on BGP. Most networks distribute their traffic, they load balance using BGP routing. And we did the same. That's how we connected to the entire world. But we needed a different mechanism. Let's say you're a user somewhere in Africa and your BGP AS path says your shortest path to Facebook is in a POP in Japan. You know that's not right. You know at a service level, that's not going to give you the performance that you want. So we needed to build a system that can measure actual network service closeness, the latency to our users from every POP in the world. And so we built a system called Sonar. You'll probably never notice Sonar, but a very infinitesimal number of profile pictures at any given time are served from POPs that we expect to perform poorly. We do this because networks change, services change, and we're continually gathering data that allows us to see the latency from nearly every network in the world to every edge cluster we have in the world. And this data set is one of the inputs for our global controller system. And this global controller system is what we use to manage the ingress traffic load for our networks. And this system has visibility to many metrics. It sees the interface utilization of every peering router in the world. It sees the BGP tables of every router. It takes this Sonar data, it takes the health of our servers, of our networks, and from this, it builds a DNS map that allows us to give different resolutions to send users, resolvers, to different POPs, either via simple dynamic DNS resolution or via generation of unique URLs per user to send their static content from the POPs that are closest to them. And all network engineers love graphs. I love graphs too. What does this mean? In the old BGP model, you have this red line where Anycast simply sends in traffic to the POP as users wake up. They exceed the capacity of our POP, and there's nothing we can do about it. All users hitting that POP get a poor experience because of this. For none of them is it good. But by having this global controller that can shift our DNS maps and pull users from this region and serve them somewhere else, we get this nice green line where we shed traffic from this POP, only serve enough that we can serve well and give a good experience for everyone. Now, at a regional level, you can see how POPs come online, users come online, and we begin to shed traffic away from all of the POPs in that region as we exceed their capacity. At a global level, you end up with multiple overlapping diurnal lines as different regions come online and go to sleep, and we shed traffic between them, sometimes needing to serve traffic from another region if we don't have the capacity in region. Now, what does this mean for all of you? It means we serve your cat videos faster. That's my new kitten. She's super cute. So how does this global targeting system interoperate with the old paradigm of a global BGP routing table? Originally, we just treated this as it was. They were ships in the night. They were unaware of each other. We could send traffic into our network in Europe and egress it on the other side of the world, and that worked well enough. BGP allowed us to enforce the simple rules that we had, prefer this peer for this set of prefixes. It worked well. But as our Sonar dataset grew, as our confidence in our global controller grew, we had an opportunity to solve other problems. We had an opportunity to improve performance, not just ingressing to our network, but also in how we egress traffic from our network. And this problem became particularly acute for us in a very serious outage, the sort of outage that you don't plan for. Multiple, diverse backbone fiber paths all failing on the same day, dramatic outage for a significant region for us. Our global controller had the opportunity to shift this traffic away from this region, serve it well somewhere else, but our simplistic BGP rules would simply pull this traffic around the world across our broken backbone, only degrading the service further. So we needed a new model. We needed to confine the domain of BGP, break it apart into city-level peering domains. And in this way, we empowered our global controllers not just to influence how we ingress traffic to our network, but also to influence how we egress traffic from our network. Now, this was not easy. It did not happen in one step. BGP solves the basic problem of forwarding very well. Software is extremely flexible, but it's also dangerous. It can do the wrong thing very easily. And we definitely had experiences with that. It was a very iterative process of learning, of finding mistakes, finding problems with our software, gaining confidence in it, slowly confining the domain of BGP, and expanding the control, the power of our controllers, the ability of it to influence and improve the performance of our service. But what we have today out of that iterative process is far more control to react to exactly these types of outages, simple network degradations, things that before we had little control over. But even on these BGP peering islands, BGP is still limited. What do we care about? We care about latency, packet loss. We fundamentally care about things that impact the performance of our service. What does BGP care about? It cares about all the attributes that we all know about. Now, you can statically encode those things as BGP attributes, but that represents just one point in time. And as we all know, networks change, services change, and that static encoding will quickly grow out of date. It'll be wrong days, weeks, months in the future. So we needed a more dynamic mechanism. We needed local network controllers. Over the next few slides, I'll take you through how we iterated through different steps, we tried different things, and how we got to where we are today. Like many, we started with host routing. It looks fantastic on slides. Use that software down in your server stack, you have complete control of every packet, you can do anything. This was not so simple for us in practice. It was not so effective for us in solving real problems. For one, you've created a new problem for yourself. You have to synchronize across a bunch of servers. In our case, a lot of servers. What if your service changes? What if you have traffic coming from somewhere you completely did not expect? And even if you solve all of these problems, and to be honest, we never fully did, you still have the most basic problem. How do you signal from your servers? How do you encapsulate this traffic to have it egress where you want from your network? We tried a few different things. We started with MPLS, two basic problems: kernel support, it wasn't there at the time, and we needed router MPLS features in every layer of our topology, from the top of rack switch to our Clos fabric switches, and the devices we had at the time just couldn't support it. So next we tried PBR, or filter-based forwarding, depending on your vendor of choice. The most fundamental problem here, you're limiting your platform diversity. You're depending on a vendor-specific feature set. And you also haven't limited your dependency on your routers. You have to manage router configuration state representing these source-based routing decisions, these mappings, and keep it in sync with your server software. And we definitely had problems with that. And if you use PBR, what bits do you use in your header to represent these decisions? DSCP is the simplest, and we actually spent the most time with that. But you only have so many bits to represent egress interfaces. It's not very flexible. We worked toward GRE key. It's a very large address space in the key value in the GRE header. But our services changed. By the time we developed this software, we had small packet sizes, a service that generated very high rates of small packet sizes as we hit peak load. And in the first weeks we deployed this new model, we crashed our two largest POPs in the world because of problems with our routers. Now, I'm sure every network engineer in this room has had this experience before. You have a problem, you have this feature or this new architecture that will solve this problem, and you do all the hard work to bring it into your network. And when you actually get there, it's like, oh, it didn't work. It didn't do what you wanted. And we are no different. We have had this experience many times. A lot of what we try does not work. If there's anything that's different about our approach, though, it's that we expect to make mistakes. We try to fail fast and to learn from it, and iterate and change directions when we need to. Now, what do we learn here? We learn to keep it simple. And what is the most simple, irreducible component of an edge network? Of course, it's BGP itself. So we evolved beyond BGP with BGP. Now, what does this mean? The most basic problem to solve, a peering router, a peer, your BGP attributes say this is the best local preference, this is the shortest AS path, I'm sending all this traffic here, but it's too much traffic and you're dropping bits on the floor. Fortunately, we have data. We have BMP exports of our routing tables. We have NetFlow data showing our utilization for every single prefix. We have link counters showing packet interface utilization and packet drops. And all of this can be pulled into our controller software. And our controller can think, where should this traffic actually go? Not limited by BGP. And then it can inject this decision as a literal BGP route, simply into our routing tables. And this is what we do today. Now, you'll note in this picture, there's only one peering router, and that's deliberate. In the original iteration of this controller model, it was very, very simple. We managed each individual peering router as an atomic object, and we could do that because our network was much simpler. At that time, we had that router God box with backbone and peering and compute connectivity. And we could expect a diverse range of peers, private peers, public exchanges, transit, all on one router. So there would be some other place to send this traffic. But if you think back to the multi-layer edge topology I showed you earlier, we now have disaggregated layers. We have many peering routers to allow us to grow faster. We can no longer expect that we'll have all of our peers on one router. Our peers could be anywhere in that city on any peering router. So we needed to move from a router level model to treating our city, our metro, as one unit, moving traffic between peering links where there's capacity across any peering routers. All the mechanisms are very similar. We inject BGP routes, but now we leak them within that city and attract traffic away from overheated links to links where we have the capacity to serve the traffic well. I'm sure you're thinking, awesome, it's all solved. We made our mistakes, we're done. Now, of course, that's never true. Nothing is ever perfect, we're never done, we always have much more to learn. And I'll walk you through a few examples of things that we needed to fix, we needed to make better, even after we moved to these models. For one, what happens if you're an IPv6 rich network connecting to another IPv6 network? IPv6 allows tremendous summarizability. You can actually encapsulate your entire network into a single v6 prefix. Now, if your controller model depends on moving BGP prefixes between peering links, if that link becomes overloaded and you move that prefix, you haven't alleviated an overload condition, you've drained your peer, and that's not at all what we wanted to do. So we needed to develop a system that would allow us to create subprefixes, just in our own local routing tables. But by creating automatic subprefixes, we had smaller chunks of traffic that our controller could manage simply, as in the old model. If the link became overloaded, we could simply inject one of those subprefixes, or several of those subprefixes, to alleviate the overload condition. Now, if you think back to earlier when I was describing the global controller, and more recently the local controller, you might have noticed that both systems are aware of link counters. They're aware of BGP tables. The local controller even influences that BGP table. And you might have asked, how do these systems work together? Initially, they didn't. They were ships in the night. They were unaware of each other. And And eventually that caused us real problems. A link could become overloaded. The local controller is very fast. It injects a BGP route, it begins moving traffic away. The global controller is slow, DNS is slow. It begins moving the DNS map at the very same moment, it just takes longer to take effect. And before you know it, we've underloaded the link. The local controller, it's very fast again, it sees this, it's moving BGP routes back into the good zone. The global controller saw the same thing, it's moving slower, and before you know it, DNS is back, we're overloading the link. And unfortunately, this could happen all day long. So what did we learn? We learned to make clear roles for our controllers, clear handoffs between them. The local controller manages our capacity within a city, and only when that city is full and there's no other place to send this traffic does our global controller engage to move traffic between cities. Okay. But oscillations can even happen within one controller, even if you don't have an interaction between two of them. In this example, our local controller is managing traffic between two peering links. And if you see the zoomed in graphic there, it's quickly moving prefixes and traffic between those links. Now, when we dug into this, what we found is the controller thought it was doing the right things, but its data was wrong. Those data pipelines I mentioned earlier, the BMP data, the NetFlow data, the link counters, all of that was built for more human consumption. It was aggregated back at global data centers. It showed up on graphs that human beings could look at. It was never built with the intention that a real-time automation system would be using it to shift traffic in a live network. So we needed to shorten those pipelines, collect this data much closer in the edge POP next to the controller, increase its granularity, its precision, and feed it fast to the controller. And by doing that, we ended up with a pretty graph you see here on the right. No network graph will be a flat line, but there's no longer any oscillations. It's managing the traffic that the interface can take well. So bringing it all together, we have a global controller that manages ingress and now egress as well, distributing it to our edge POPs. Within those edge POPs, we build multi-layer topologies, and we manage our egress traffic with a local network controller. And we're by no means done. We have more work to do, increasing the modularity of our network, the resilience in our layers, building more diversity in our networks and systems to work around failures faster. We want to increase the programmability of our network. You might have heard about efforts like OpenR, which has applications in wireless mesh networks or our backbone, but we believe also has an important place in our edge networks, moving beyond the old paradigm of fixed routing protocols and standards committees and asking vendors for features, but allowing us to quickly iterate and try new things, to marry a programmable network with our software systems. And last but not least, performance. I talked earlier about Sonar and how we use performance data to improve our service and improve how we forward traffic. We actually have much more data than we use today. Now, edge networks are not like data centers. They're not simple. There's a lot of noise out there on the internet. But we believe there is still signal that we can pull from this noise, using this more programmable network with our software to make better forwarding decisions and to improve the performance of our service for the people who use our products. Now, if you take away anything here today, I would like it to be that we did not have all the answers. We did not know where we would end up when we began. We started small, we tried things, we tested them. We had a lot to learn. But the thing that I hope does not change is our values. We value operations, practical experience, over abstract features and fail-safe architectures. We try things, we iterate, we test them. We're willing to make mistakes and learn from them so we can make a final solution that's better. But there is no final solution. Where we are today is not the end. We have much more work to do. It can be done better, and we know that. Now, I'm sure many people in this room have problems that are very similar to the problems that we have. And you may have different solutions, different approaches. In fact, I hope that you do. And if you do, we would love to talk to you. Please seek us out. We would love to chat. Thank you very much. Any questions? Either.
My name is Linda Dunbar from Huawei. That's a very interesting presentation.
Thank
I
you.
do have questions about this local control.
Sure.
In IETF, there's a working group called I2RS, Interface to Router, that helps router to change the policy on the route. There's also IDRs on the BGP flow spec. Do you use any of those standardized approach?
We do not. We use simple BGP.
You use simple BGP.
Our injections are vanilla V4 and V6 prefixes and nothing more.
Okay, and you don't use flow spec, BGP flow spec to
We do
change
not.
route?
No.
Okay.
It's very simple. Very
Thank
simple.
you.
Literally just IPv4 routes, IPv6 routes, and nothing more.
Thank you.
You're welcome.
Hi.
Hi there.
Naveed here. In the last slide, you mentioned that you're not relying on the interface counters or the data provided by the NetFlow as a measured input to your controller for real time. So I was wondering.
We are using NetFlow and link counters as an input to our controller.
Okay, but they were resulting in the overflow, right? As I understand, because they were not real in a real time fashion.
Yes, so we improved that collection. We actually moved the collectors from our central data centers. Instead of collecting them globally, we actually spawned collectors in every single one of our edge POPs in the world. And we increased the granularity of those collectors so that we could provide very precise data in the same city, actually in servers adjacent, directly to our controllers so that they have real-time data to act on. Does that make sense?
Yeah.
Cool.
Sounds good. Thanks.
You're welcome. Any more questions?